And in this video we're going to take a look at reflection, one of the ways that waves interact with barriers. Reflection occurs when a wave hits a barrier and bounces off of it, reflects off of it, thus reflection. Reflection is governed by the law of reflection, which states the angle of incidence equals the angle of reflection. That definition in and of itself is not a very useful one unless, of course, you understand what angle of incidence and angle of reflections are. So let's start with that. What I have here is an illustration of reflection. This is my reflective surface, or the mirror in this case. And what I have here are two rays that are drawn, one hitting the mirror, one bouncing off. A ray is a point on a wavefront. As a wave approaches this mirror, like light, it's a series of crests and troughs approaching the mirror. And what we're doing here is we're selecting a point on that wavefront and following that point as it hits the mirror and then bounces off of it. The ray that hits the mirror is called the incident ray. The ray that bounces off the mirror is called the reflected ray. So incident is the wave that is approaching the mirror. Reflected is the wave that is bouncing off the mirror. There's an imaginary line that's drawn right here called the normal. The normal is a line that is perpendicular to the reflective surface, drawn at the point of incidence, or the point in which our ray actually strikes the mirror. Now for the important part. The law of reflection says the angle of incidence is equal to the angle of reflection. Both of those angles are measured against the normal. We take the angle produced by the incident ray and the normal. That angle is called the angle of incidence. We take the angle produced by the reflected ray and the normal, and that is called the angle of reflection. So again, the law of reflection states that the angle of incidence is equal to the angle of reflection. So this angle produced by the incident ray and the normal, is going to be equal to the angle produced by the reflected ray and the normal. Now, one of the things that's kind of tricky about this is if I were to ask you to illustrate reflection with an angle of incidence of 30 degrees, you got to be careful that you measure the right angle. This would be that 30-degree angle, not over here. We'd have 60 degrees over here. Again, because angle of incidence is always measured from the incident ray to the normal, is this angle that we're talking about. The way that I would suggest you draw such a thing is by getting a protractor, laying down the base of that protractor against the reflective surface, the mirror. I would suggest you make 3 marks on your paper. Well, 4 really. Mark the center of your protractor, the center of the base. Mark where 90 degrees is. And then go 30 degrees this direction, 30 degrees this direction from 90. So basically you're going to come over here to that 60-degree mark and make a point. Come over here to the 60-degree mark and make a point. Again, because we need to be 30 degrees from the normal. And then take your protractor away. Draw in your normal as a dashed line. Draw in your rays, reference to those other 2 points that you put on the paper. So again, that's your potential tricky part. Again, incident ray is the incoming ray, that point on the wavefront that we're following in through the process. The reflected ray is the one that bounces off. The point of incidence is the location where the incident ray strikes the mirror. So wherever this ray hits the mirror, that's the point of incidence. The normal is the imaginary line drawn perpendicular to your reflective surface, 90-degree angle, at the point of incidence. The angle of incidence is the angle between the incident ray and the normal. Angle of reflection is the angle between the reflected ray and the normal. The big optical device that we talk about when we talk about reflection will be mirrors. And we need to understand the way planar mirrors convex mirrors and concave mirrors work. Mirrors are simply reflective surfaces that redirect light rays or reflect light rays. They produce images that are either going to be real or virtual. And the first thing you want to understand is what real and virtual images are. Let's start with a real image. A real image would be produced in front of the mirror and can be projected onto a surface like a piece of paper. So here's the way it would work. I'd be standing here. The mirror would be over here. The image is somewhere between me and the mirror. That's what I mean by in front of the mirror. The image would be somewhere between me and the mirror. And if I held a piece of paper up, I'd be able to see that image on that piece of paper. It would be a projected image. Real images are in front of the mirror and can be projected onto a surface. Real images are upside down. So again, I'd be here, mirror be here, paper would be here. The image that's on the paper would be upside down. So real images are in front of the mirror and they're flipped upside down. Virtual images are produced behind the mirror and cannot be projected onto a surface. So this is like looking in the bathroom mirror in the morning. I'm standing here, mirror's here. The image I see of myself appears behind the mirror. And in the bathroom mirror is the same distance behind the mirror as I am in front of it. So if the mirror's here and I'm 2 feet in front of the mirror, my image would appear 2 feet behind the mirror. That's what I mean by behind the mirror. It cannot be projected. So no matter where I hold a piece of paper, I'm not going to see an image. It's not a real image. That's why it's called a virtual image. So virtual images appear behind the mirror. They are always upright. So the head would be up, the feet would be down, always upright. But they are flipped left to right, which you've seen before if you've ever been driving or riding in a car and looked in the rearview mirror. Anything that's written, any text that you see is always backwards because it's being flipped or reversed, left to right. Let's take a look at the types of images. There's 3 main types of mirrors produced: plane mirrors, convex mirrors, and concave mirrors. A plane mirror is a flat mirror. So like the one that's in your bathroom. Plane mirrors produce virtual images that are unmagnified. So what that means is, again, virtual. If this is my real object here, my image is going to be behind the mirror. That's virtual. It's going to be upright. So if the arrow is pointing up here, the arrow is pointing up over there. It's the same orientation as the original object. So it's behind the mirror. Object's here, image is here. It's behind the mirror. It's in the same orientation as the original object, so it's upright. And it's unmagnified. So the size is the same for both the real object and the image. And again, these are like bathroom mirrors. So again, plane mirrors produce a virtual image. Virtual means behind the mirror, upright, and reversed left to right, those 3 things. And unmagnified, it just means it's the same size. If a mirror is not flat, that means it's curved. And the first type of curved mirror we'll look at is a convex mirror. Convex mirrors are curved outward or towards the actual object. So this is my real object here, and it's kind of hard to see in this, so I'll exaggerate it a little bit. It's curved out towards the object. That's what curved outward means. It curves towards the actual object. Convex mirrors produce virtual images. So again, virtual means behind the mirror, upright, and reverse left to right. So here's my real object here. Here's my image over here. The image is behind the mirror. My arrow is pointing up on this side for my real object. My arrow is pointing up on my image as well, so it is upright. It would be reversed left to right. But note here there's a size difference between the two. In a convex mirror, the image is reduced. So this is the size of my original object. That's the size of my image. My image is smaller than the real thing. An example of this type of mirror would be the passenger side rear view mirrors of a car. The passenger side rear view mirrors of a car say images are closer than they appear, or objects are closer than they appear. When you look at a car in the rear view mirror on the passenger side, it appears further away than what it really is because the image is reduced. It's smaller than actual size. And our brain equates smaller images with things that are further away. So when we look in that passenger side rear view mirror, the cars that are there appear further away than what they really are because the image is reduced. It's smaller than actual size. They do that to provide a wider field of view. They do that to help with blind spots. So you can see more in that mirror. But the cost for seeing more is the reduced size of the image. The final mirror type is the concave mirror. Concave mirrors are curved inward, so they curve the opposite direction of a convex mirror. They move away from the actual object. They're complicated. And the reason why the concave mirror is more complicated is because it actually has something called a focal point. A focal point is where the reflected rays from the mirror will intersect or converge. They'll come together. Concave, converge in this case. Won't mean the same thing when we do lenses. But the light rays will come together on a point. That point is called the focal point. Here's an illustration of what that looks like. So this ray comes in, hits the mirror, bounces in this direction. This ray comes in, hits the mirror, bounces in this direction. And all those rays meet at that point. That point is called the focal point. The type of image that a concave mirror will produce depends on where the object is relative to that focal point. If the object is outside the focal point, and that's just another way of saying further away from the mirror than the focal point. Focal point of this mirror is right there. Object is outside of that focal point, further away than that focal point. When that happens, you're going to get a real image. And this is the only scenario that produces a real image in a mirror situation. A real image, again, is going to be in front of the mirror. So there's my object, there's the mirror, the image is right here. The image is in front of the mirror. And virtual images are behind, real images are in front. So when I say, when the object is outside of the focal point, it produces a real image, that means the image will be in front of the mirror. It will be upside down. So you know my arrow points up here, and if you can see, it might be hard to see, the arrow is pointing downward on my image. This arrow is pointing up, this arrow is pointing down to indicate my image is upside down. And it's real, it's projectable. If I held a piece of paper here, I'd see that arrow. I'd have a real projectable image. So again, when I say real image, that means in front of the mirror, upside down, and projectable. You can actually see it on a piece of paper. Size-wise, it is reduced. You'll see how large the object arrow is. You see how much smaller the image arrow is. That is a reduced image. An example of this, where this would be utilized, would be in reflecting telescopes. In a reflecting telescope, there is a concave mirror in the very back of the tube. So what you have is a long tube, and at this end you have a concave mirror. Up in the front, you have a smaller secondary mirror, and that's where the eyepiece goes. So what happens is light rays come in, bounce off, hit this mirror, come back to the eye, and it's up in here that you have your focal point. It's up in the eyepiece that you make your image. It projects an actual image for you to see on your retinas, for your retinas anyways. The reflecting telescope is an example of an object that uses one of these concave mirrors where the object, obviously out in space, is well beyond the focal point of that mirror. It produces a real image, one that is reduced in size but then magnified by your eyepiece so you can see it. If your object is inside the focal point, and again, we have to know where the focal point of this mirror is. And in this illustration, the focal point is right there. My object is right here. So my object is in front of the focal point. It's between the mirror and the focal point. So my first case scenario, the one at the telescope, the mirror is here, the focal point is here, the object is here. What we're doing here is we're flipping the focal point and the object. So it's mirror, object, focal point. When it's set up in this scenario, the image is virtual. So again, you've got to remember all the things that virtual means. Virtual means behind the mirror. It means upright. It is flipped left to right. You cannot project it on a piece of paper. That's why it's called virtual. And we see all that here. Here's my object. It's an arrow pointing up. There is my image. My image is behind the mirror. It's upright. This arrow points up. That arrow points up. What the illustration cannot show us is the flipping from left to right. This is a magnified image. You'll see that the object arrow is smaller than the image arrow. The image is larger. This is a magnified image. These are used in makeup mirrors, the kind that make your face look bigger so you can see where you're putting your eyeliner and things like that. It gives you a larger image of your eyes so you can put on your makeup more easily. That's it for reflection. There's no real math here other than measuring angles and drawing the illustrations.